Hello, and welcome to the Chapter 15.7 lecture on maximum and minimum problems. So, given a function that's defined on some domain, an absolute minimum or maximum is a point AB, so that the valuation of the function at that point is greater than or equal to f over the entire domain of the function. And it's an absolute minimum if it's less than or equal to the function everywhere else. And a local minimum or a local maximum is one that is less than or equal to the value of the function everywhere in some disk around that point. So for example, this is a local minimum, but this is both a local and absolute minimum because it's the lowest point overall. And note that the inequality here is a less than or equal to or greater than or equal to. So that means that technically on a horizontal plane, every point would be both a local minimum and a local maximum, and also a global minimum and global maximum because of the non-strict inequality. Derivatives and local maximum and minimum problems. So recall from Calc 1 that at a local minimum or maximum of some function, then the tangent line is of slope 0, and the derivative of it at a local minimum or max is 0. Okay, well, the same things are true here, but with partial derivatives. If f has a local minimum or maximum at a point, then the partial derivatives, both f sub x and f sub y, are 0, because at a local min or max, then your tangent plane is a horizontal plane. And note that while this condition is necessary, it is not sufficient. It is possible for both of these partial derivatives to be 0, and yet it not be a local minimum or maximum. And here's an example of how. It can be what we call a saddle point. So this hyperbolic paraboloid has what we call a saddle point right there. Both the partial derivative in the x direction and that in the y direction are 0 at this point, because the derivative of a parabola is 0 at the vertex. But it's clearly not a local minimum or maximum. And a critical point is a point where the two partial derivatives are 0, or one of them does not exist. So a critical point could be either a local minimum or maximum or a saddle point. And to min or max a function, we'll be finding the critical points and then doing some analysis on them to determine which of these conditions it is. So let's do an example. So to find the critical points, what we want is that both partial derivatives are 0. So let's find those partial derivatives. So del x of this function is del x of this. I've just FOILed this out to make it easier to find the partial derivative. And that is 2xy minus y. And that's right, that is 2x minus 1 times y. Okay, and del y of f is just x times x minus 1. Okay, and what we wanted was for both partial derivatives to be 0. And what we wind up with is a system of equations. So we want to find all xy that satisfy both of these simultaneously. Now, the reason that we factored up here was to make solving this easier, because if the product of two things is 0, then one of them has to be 0. So this first guy implies that either 2x minus 1 is 0, or y is 0. And that's the same as x is negative 1/2, or y is 0. Okay, and the second guy, that implies that x is 0, or x minus 1 is 0, so x is 0 or 1. Okay, and how do we progress from here to finding all pairs? Well, we can do an analysis. Okay, so if x is negative 1/2, so in this case, then this can't possibly be true. So that means that it must be the case that y is 0 from the first part. And now x equals 0, or x equals 1. So in total, we have that our possible critical points are 0, 0, and 1, 0. And the point of this example will be that sometimes we can see things and we need not solve the system. So taking the partial derivatives here, we get this and that. Okay, but look at this. The second guy is 2x plus 2y minus 1, and the first guy is 2x plus 2y minus 1. those are the same. So we just have 2x plus 2y minus 1 equals 0 is all critical points, and that is infinitely many. It's that whole line. Okay, and how can there be a whole line of critical points? Well, it turns out that this is a parabolic sheet. Okay, so to the best that my artistic ability allows, it looks like this. It's a parabolic cylinder, was the term that we learned. And then it has infinitely many maxima, namely everywhere along the ridge. So it's like an infinitely long ridge, and all of those are critical points. Now, we'll be using determinants, and we already encountered determinants. So recall that given a 2 by 2 matrix, A, B, C, D, its determinant is AD minus BC. And the determinant is geometrically the signed area of the parallelogram made by the vectors AB and CD, the two rows. And in the sense that this determinant is always this area in magnitude, and is positive if there's a counterclockwise motion between them, and negative if there's a counterclockwise motion between them. This will be important in a bit when we get to Jacobians, a good deal later on in the course. And what we want to do is determine if critical points are not saddle points, because a saddle point that's the case where a critical point is neither a local minimum nor local maximum. And the idea is that a point is a minimum or maximum if both the second partial derivatives have the same sign. In other words, it's both curving up or both curving down in the directions of the two partial derivatives. So like here, it looks parabolic in both the x direction and the y direction. Both of those second partial derivatives are positive. And the two mixed partial derivatives are neither great enough to override the local trends set by the non-mixed second partial derivatives to make the directional derivatives vary in sign. So illustrated it right, the second partial derivatives do override the positive trends in the pure x and pure y directions, because over here it's facing down. This is still the saddle point, even though f sub xx and f sub yy are both positive. And that's because del x, del y is great enough in the negative direction to override that in this directional derivative. And what we can do to formalize this idea is consider the product of f sub xx and f sub yy, and then we subtract the product of f sub xy and f sub yx. And this guy, that will be negative if and only if the mixed partial derivatives do override the non-mixed partial derivatives. So if this guy is negative, then we'll be in the overriding case, and it will be a saddle point. While if this guy is positive, then these guys aren't strong enough to override these, and it will be a local minimum or maximum. And looking at this, which is the same as this by Clairaut's theorem, it's the same as this by the definition of our determinant. So we'll be considering the determinant of what's called the Hessian matrix, this guy. And here's our theorem, the second derivative test. So suppose that the second partial derivatives of a function are continuous throughout a region about our critical point AB. And let d of xy be this guy that we just defined, the determinant of the Hessian matrix. D is just this guy. Then if that is positive, then we are in the case where this guy is weak and there is no overriding, and then it is a local minimum or maximum. And whether it's a local min or max just depends upon if the second non-mixed derivative is negative or positive. If the second non-mixed derivative, it could be either f sub xx or f sub yy, it doesn't matter, they write f sub xx, is negative, then that means that it looks like this. That is a negative second derivative because the slope is decreasing. And then we have a local max. On the other hand, if there's no overriding, the determinant of the Hessian is positive, and the second partial derivative is also positive, then that means that the slope is increasing. So it looks like that, and is a local minimum. And if the determinant of the Hessian is negative, then that means that we would be in the strong case. And then there is an overriding here, and it makes it look like this, and it is a saddle point. And if the determinant of the Hessian is 0, then the test is inconclusive. Fortunately, that will seldom be the case. So let's do an example. Let's find and classify the critical points of this. Okay, so earlier we found that the critical points were 0, 0, and 1, 0. And now we find d of xy. D of xy is f sub xx, f sub yy, minus f sub xy squared. So we compute those guys. Okay, so f sub xx is del x of 2x minus 1 times y. We found this first partial derivative earlier. And the determinant of that with the derivative of that with respect to x is just 2y. Okay, and f sub yy is del x of x times x minus 1. And that's a nice calc 1 derivative. And that is 2x minus 1. And finally, f sub xy that would be del x of del y. Okay, and f sub y, that's del y of del y. Del y of this is x times x minus 1. And now all of this is constant with respect to y. So del y of that is 0. And f sub xy is del x is del x of x times x minus 1. And that's a nice calc 1 derivative, which is boiling out and taking the derivative 2x minus 1. Okay, so thus our d of xy, determinant of the Hessian, is f sub xx, f sub yy, that's 2y times 0, minus f sub xy squared, 2x minus 1 squared. and that is negative 2x minus 1 squared. So we have found f sub x is 2y, and d of xy is negative 2x minus 1 squared. Okay, now what we do is we test each of these points according to this test. Okay, so at 0, 0, don't plug it into f sub xx first. You should always first test which of these cases you're in. Because if you're less than 0, then there's no point in plugging in. It's just automatically a saddle point. So at this point, then d of 0, 0, that's negative 2 times 0 minus 1 squared, is negative 1. And that is less than 0. In other words, we are in case 3. So that means that 0, 0 is a saddle point. And let's test our other point. At 1, 0, we wind up with the same thing. So 1, 0 is a saddle. And here's a picture of what the function looks like. So we found that 0, 0 and 1, 0 are saddles. And you can see that indeed, both of those two, which are our only two critical points, are saddles. And you can see this function has no local minima or maxima, just those two saddles. So here's an example with several more critical points. What we can do is once we find our critical points in the way that we have learned how to do, then we can make a table listing our various critical points. And then for each critical point, we can list that determinant of the Hessian, the d of xy, the same d of xy that's in the second derivative test. And then for each of those, list the f sub xx, and come to a conclusion about what each one is. And this is a nice way of just getting everything in one spot. So for these first two and the last two, then the d of xy is negative. That means that it's automatically a saddle. And then here it's positive, and f sub xx is negative. That would mean a decreasing slope. So it's therefore a local maximum. And here's a picture of what this function looks like. So it has these 4 saddle points around this local maximum, and there is its map of level curves. Now we can also find absolute minima and maxima. And one thing I want to illustrate is making a table to find not just local minima and maxima, but absolute ones on some domain. Suppose that hypothetically we have some function f of xy in which we find these 4 critical points, and we want to find its absolute minima and maxima. Well, we can make our list of critical points, find our d of xy for each of those, and here we would have negative d of xy, so that would automatically be a saddle. Here we have positive d of xy, and the slope is increasing, so that would look like this. That would mean it's a local minimum. While for the next two, the slope is decreasing. That would mean both of those are local maxima. And suppose that the question asked us, what are the absolute minima and maxima? Well, then we could take our various critical points and plug them back into the original function. And suppose that we get, say, minus 3,297 as the outputs of these guys when plugged into f of xy. Well then, that would mean that minus 3, this would be the absolute minimum occurring at 1, 2, and then the 9 here, that would be the absolute maximum occurring at 3, 2. And the 7 would be a local maximum, but not an absolute maximum. And the 2 there is just the value of the saddle point, which is never going to be a local min or a local max. Okay, now, sometimes we are interested in maximizing or minimizing functions that are restricted to some domain. And back in Calc 1, you might have had a function that you restricted to be between 2 points a and b. Well, it's the same thing here, except now our restriction of the function isn't just between a and b, but within a whole closed bounded region. And then we can talk about the absolute maximum or absolute minimum of the function on that domain. And the key difference is that now minima and maxima can occur not only where the minima and maxima can occur not only where we have a critical point, but also at points along the boundary, which may not be critical points of the entire function extended to beyond the boundary. In the same way that if we look here, this would be a local max, and this would be a local min back in Calc 1. However, the absolute maximum would be at the boundary and not a point where the derivative of the function was 0. So in other words, not a quote critical point in the Calc 1 sense. So the same thing can happen here, where we can have minima or maxima along the boundary that are not critical points. So for a theorem on which ones have minima and maxima, we need to recall what a closed set is. Here is just a nice quick way of thinking about it. If we have a unit circle where we can be everywhere inside of it, but not on its boundary, so that'd be x squared plus y squared is less than 1, but not equal to 1, then that is what we call an open set, while a closed set is a set that includes its boundary. So x squared plus y squared is less than or equal to 1, a closed set. The point is that it includes its boundary. Okay, so it's very much like, by the way, on the real number line, we can have an interval AB that does not include its boundary, or an interval AB that does include its boundary. It's the same deal, except now these are two-dimensional figures. Okay, and our theorem will be that closed bounded sets, so in other words, sets that, well, are closed and bounded in the sense that they don't extend out to infinity in any direction. If those are the domains of a function, then, and that function is continuous, then it will necessarily have an absolute maximum and minimum on that domain, possibly at one of the boundary points. And the way to find those absolute minima and maxima is to determine first all critical points of f in the region R, that is this domain, find all maximum and minimum values of f on the boundary of R then, and then the greatest function value found among these is the absolute maximum, and the least one is the absolute minimum. So in other words, we would go through and make a list very much like this, except that now, in addition to our critical points, we might have a final boundary point. And along the boundary, then it would be a matter of calculus 1. It could be a difficult calculus 1 problem, but the point is that the boundary would be a line of some kind. And maximizing along the line is a matter of single variable calculus, and we would have a maximum or minimum of that with a particular value, and then we would find where the function is maximized just along the whole expanded list. It could be inside of the region, or it could be at one of the boundary points. So here's a picture of what we're talking about. Here's a function, and suppose that we want to maximize it within this closed bounded domain of the unit circle being less than or equal to 1. Well, pictographically, you can see that it seems to have an absolute maximum right there, and then it has a saddle point there, and two minima at the boundary points. And at these boundary points, then it's certainly not a critical point of the function overall, but that's still a minimum and it occurs along that boundary. So we make the list with these points that are listed here and find which of those is the maximum and which of them is the minimum or minima. And again, the way that we would do that is first to find the critical points, which are everything not on the boundary that could be a min or a max, and then find the mins and maxes along the boundary by a variable substitution, for example. And in fact, we'll be learning very soon just a slick way of doing this. So don't worry too much at the moment about maximizing along a boundary. Okay, but just to illustrate how we could do it in a calculus 1 way, suppose that we wanted to find the absolute minima and maxima of this within the unit disk. Okay, well, so along the boundary, just to illustrate, that would mean that we have x squared plus y squared equals 1. That would mean that y squared is the square root of 1 minus x squared. And what we could then do is just substitute this whole guy in for y everywhere. And we would have that z is equal to x squared plus y squared is now this minus x minus y is that, etc. And the point is that we get a function of just a single variable So minimizing or maximizing along the boundary is really calculus 1 in this sense. And to min-max this along the boundary of the unit disk, we would just differentiate this and set it equal to 0, and that would do it. And then to find the mins and maxes within the unit disk, we find the critical points and do exactly the procedure that we have done this video lecture. Now, that works, it completely works in every way. It's just that differentiating this looks awful, doesn't it? Well, fortunately, in the next section, we will be learning the method of Lagrange multipliers, which will be a very nice way of minimizing or maximizing a function subject to a constraint, like the constraint of being along a boundary, and it will save an algebraic mess. So that concludes this lecture. Have a great one.